Section 6.1 is our last section that helps us with graphing, and it's looking specifically at rational or fraction functions and inequalities. Now, if you'll remember when we were working on our common graphs, f of x equal to 1 over x was a common function that we should know the graph of. In fact, we said that its graph would be a boomerang in the first and third quadrant. So graphing this, we know it looks something like that. Now, if it had been an x squared or an even exponent on the bottom, you remember it would be a boomerang also, but it would be in the first and second quadrant. So when you have these rational functions, the graph is going to be some type of boomerang somewhere. Now, we didn't mention it before, but we do need to look a little closer at the graph of this rational function. We have these boomerangs, but more importantly, the ends of the boomerangs approach a line. They get very, very close to that line, but they never cross it. That line is what we call an asymptote, and there are several different types of asymptotes. You have a vertical, a horizontal, and a slant asymptote. We only work with vertical and horizontal in this class, but again, an asymptote in general is a line that your graph gets very, very close to, but never touches or crosses. So if you'll look at this graph that we have here, you should agree the horizontal asymptote is going to be this x-axis. It gets very, very close to the x-axis on the ends of our graph, but it never touches it or crosses it. Also, if you'll look at the middle of the graph, you should see that we have a vertical asymptote on the y-axis. Again, in the middle, the graphs get very, very close to that vertical asymptote, but never touch it or cross it. Now, it's our job in this section to be able to find those asymptotes to help us with our graphing. To find vertical asymptotes, first off, you do need to factor the denominator if you can. If there's anything to simplify, you need to do that as well. And then once you've simplified it, you'll take each remaining factor, set it equal to 0, and solve for x. So in this problem, if you'll notice, the denominator does factor as x plus 3, x minus 3, but nothing can simplify, so we're going to take each factor in the denominator, set it equal to 0, and solve for x. So that would tell us we're going to have a vertical asymptote at x equal to negative 3 and x equal to positive 3. This next one, x to the third, divided by x squared minus 4x minus 5. Factor in the denominator, this would factor to be x minus 5 times x plus 4. Nothing can be simplified, so we can find our vertical asymptotes by taking the factors in the denominator, setting them equal to 0, and solving. So this would give us the vertical asymptote of x equal to 5, and another one at x equal to negative 4. Your next example. This denominator can factor by taking out a greatest common factor of 2x. It leaves you x minus 4. Now, if you'll notice, you can factor the x on cancel the factor x and the factor x on bottom. So that means it'll simplify to give us just 1 over 2 times x minus 4. Now, once you've simplified it, taking any remaining factor in the denominator, setting it equal to 0, would give us our vertical asymptote, which is 4. Now notice we didn't do anything with the 2. The 2 is a constant. It does not have a variable, so you could not solve for x because there is no x with the 2. Alright, now one more. 9 over 3x squared plus 7. 3x squared plus 7 cannot factor. So if we take that denominator and set it equal to 0 and have to solve this, noticing that it's quadratic, that tells me I'm going to have to use one of my other methods. I'm going to use the something squared equal to a number method by subtracting 7 and dividing by 3 to get the x squared by itself. Now remember, with that method we take the square root of both sides, but immediately you can see the square root of a negative will be I, which is imaginary, and we are only graphing real things, so you would tell me that there is no vertical asymptote here. Now, to find the horizontal asymptote, it's a little different. There are 3 rules that you have to learn, and they're all based on the degree of the numerator and the denominator. Remember, the degree is the highest exponent. Now, if the degree of the numerator is less than the degree of the denominator, y equal to 0 is your horizontal asymptote. If the degree of the numerator and the denominator are equal, then your horizontal asymptote is going to be y equal to p over q, where p and q are your leading coefficients of your numerator and denominator. And then if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Now, there's really no way to prove this to you. It does require calculus, so if you're planning on taking calculus, you will go back through this and learn exactly why these rules are set up for us. But for this class, all you'll need to do is just memorize these rules. Alright, so finding the horizontal asymptotes on this. If you'll notice, the degree of the top, remember that's your highest exponent of your variable, is a 1. On the bottom, the highest exponent is a 2. Since the top is less than the bottom, we automatically know that the horizontal asymptote would be y equal to 0. On the second one, the degree of the top is a 1. The degree of the bottom is a 1. So that tells us our top and bottom are equal. When that's the case, remember your horizontal asymptote is going to be the leading coefficient of the top, which in this case is 6, divided by the leading coefficient of the bottom, which is 2. And that can be simplified to give us 3. So y equal to 3 is our horizontal asymptote. This third one, the degree of the top is 3, the degree of the bottom is 2. That tells us the top is bigger than the bottom. Anytime the top's bigger than the bottom, that tells us there is no horizontal asymptote. This next one, on top we don't have a variable, so that tells us our degree is 0. On bottom, the degree is 2. So the top is going to be less than the bottom, so automatically we know the horizontal asymptote would be at 0. Alright, now in these next few problems, they are asking for both the horizontal and vertical asymptote. So looking at this first one, cannot factor the denominator, cannot simplify. So to find the vertical asymptote, we're going to take the denominator, set it equal to 0, and solve for x, so we get a vertical asymptote of x equal to -3. To find the horizontal asymptote, we're going to look at the degrees. On top, the degree is a 2. On bottom, the degree is a 1. That tells me my top is bigger than the bottom, and when the top is bigger than the bottom, that tells us there's going to be no horizontal asymptote. On this next one, the denominator can factor as x plus 5, x minus 5, but nothing will cancel. So to find our vertical asymptote, we can take each factor, set it equal to 0, and solve. So we get 2 vertical asymptotes at -5 and at 5. To find the horizontal asymptote, you look at your degree. On top, it's a 1. On bottom, it's a 2. So that tells us our top is less than the bottom. And remember, if the top is less than the bottom, your horizontal asymptote is going to be y equal to 0. For this next one, the denominator will factor as 2x minus 7 times x plus 1, but nothing cancels. So to find our vertical asymptote, we'll take each one of those factors, set it equal to 0, and solve. We'd get a vertical asymptote at 7 over 2 and at -1. To find the horizontal asymptotes, we'll look at our degree. On top, it's a 3. On bottom, it's a 2. If the top is bigger than the bottom, that tells us we will have no horizontal asymptote. And then this last one. The denominator cannot be canceled, or factored, excuse me. So we'll take that factor, set it equal to 0, and we would get x is equal to -9. Horizontal asymptote, the degree of the top is 1, the degree of the bottom is 1, so that means our horizontal asymptote is going to be the fraction of our leading coefficients. So on top it's a 2, on bottom it's a 1, so we can simplify that to be 2 over 1. Now, we just got through working on vertical and horizontal asymptotes for our rational functions. Now we need to look at our rational inequalities and figure out how to solve those. You do need to rearrange your problem to where 0 is on one side. You'll take the numerator, set it equal to 0, and denominator and set it equal to 0, and this will give us what we call our critical values or critical points. And it is only at these critical values or critical points that a graph can change from being positive to negative. Now you will put these values on a number line, and then we'll do a sign test. We're going to test the function at some number in each one of the intervals to see if we get a positive or negative answer. Now once we've done this, we do have all of the answers, and then we would then only use the answers for the question. So let's look at this first one. X minus 5 over x plus 7 is less than 0. Now they've already set it to 0 for us. So we're going to take the numerator, set it equal to 0, and that would give us 5. Take the denominator, set it equal to 0, and that would give us -7. Now these are what we call our critical values or critical points. They need to be placed on the number line correctly. So of course -7 is smaller than 5. So we'll put the -7 on the left, the 5 on the right. Now what this does is it divides our number line into 3 parts. All the numbers that are to the left are less than -7, all the numbers between -7 and 5, and then all the numbers to the right of 5. Now we need to pick one number that's in each one of those intervals, test it to see if we would get a positive or negative answer. So if I needed to find a number to the left of -7, we could plug in -8. So if I let x be -8, I would get -13 over -1, which would be a positive 13. Now we're not as concerned as much about the 13 as we are the fact that you got a positive answer. Some number in between -7 and 5, I could use 0. So if I let x be 0 on top and bottom, I would get a -5 over 7. And again, we don't care about the 5 over 7, but we are interested in the fact that it is a negative answer. And then one more, if we let x be some number to the right of 5, which would be 6, we would get 1 over 13, which again is positive. So by doing the sign test, we know everything. We know that if we take an x value to the left of -7, we would get a positive answer. If we plug in x values between -7 and 5, we would get a negative answer. And if we plug in x values bigger than 5, we would get a positive answer. Now, looking at your question, they are asking for where this is less than 0. Less than 0 is negative. So that's going to occur in this second interval. That second interval is in between -7 and 5. So we would write this as -7 to 5. All right, this next one. Again, they've already set it to 0 for us. So we'll take the top, set it equal to 0. Take the bottom, set it equal to 0, and solve them to get our critical values. So getting your critical values, we would get a -7 and a -3. Putting those on our number line, -7 is smaller, so it'll go to the left. -3 is larger, so it'll go to the right. From this point, we do need to do our sign test. Picking some number to the left of -7, we could try -8. Plugging in -8. Be careful of your signs. Negative times a negative would give us a positive 8 minus 7, which is 1. -8 plus 3 is -5, so that would give us negative answers. In between -7 and -3, we could try -4. Again, watching your signs, negative and negative would make that 4 minus 7, which is negative 3. Negative 4 plus 3 is negative 1, which would give us a positive answer. And then one more. To the right of negative 3, we could plug in 0, which would give us negative 7 over 3, which would be negative. So again, once you've done the sign test, you know it all. You know where it's positive, you know where it's negative. Now we got to answer the question. They want to know where this is less than or equal to 0. Less than or equal to 0, remember, is negative numbers. So that occurs in this first and third area. That first area is to the left of negative 7, so we would write it from negative infinity to negative 7. Now, we know infinities always use parentheses. Because of our inequality sign, we would use a bracket. But now let's pay attention to the next area. The next area is to the right of negative 3. So that would be from negative 3 to infinity. Again, we know infinities always use parentheses, but this time we've got to look not only at the sign, but also the fact that it's a fraction. Yes, the inequality sign tells us we should use a bracket, but that bracket would mean that we are including the negative 3 in our answer. But if you try to plug in a negative 3 in that denominator, you're going to get 0, which is undefined. So because it's a fraction, we cannot include that negative 3, so we would have to put a parentheses around it. Alright, this next one. The top you can factor as x plus 3 and x minus 2 to help you find your critical values of negative 3 and 2. Taking the denominator and setting it equal to 0, you would get a third critical value of negative 1. So putting those on the number line, negative 3 is the smallest, then negative 1, and then positive 2. So this time, since we have 3 critical values, you have 4 areas to test. So we'll start with the first one. To the left of negative 3, we could use negative 4. So if I plug in negative 4 into my function. All right, negative 4 squared is 16, minus 4, minus 6, and then on bottom we got minus 4 plus 1. 16 minus 4 is 12, and 12 minus 6 is 6. Negative 4 plus 1 is negative 3. That's going to equal a negative 2. We really don't care about the 2, but we know we're going to get a negative answer. In between negative 3 and negative 1, I could try negative 2. Plugging in the negative 2. Negative 2 squared is 4. Now 4 minus 2 is 2. Minus 6 is negative 4. On the bottom, negative 2 plus 1 is negative 1. So that would simplify to be a positive 4. In between negative 1 and 2, we could use 0. That would give us negative 6 over 1, which is negative 6. And then last, plugging in some number to the right of 2, we could try 3. Three squared is 9. So 9 plus 3 is 12, minus 6 is 6. 3 plus 1 is 4. That simplifies to 3/2, but more importantly, it's positive. So again, we know it all. We know where it's positive. We know where it's negative. Now we need to answer the question. They want to know where it's less than 0. So again, that means where it's negative, and it's negative in 2 spots. To the left of negative 3, which would go from negative infinity to negative 3, and then in between negative 1 and 2. And we are using parentheses on all of those because of that inequality sign. All right, now let's look at this last one. If you'll notice, they did not set it to 0 for us, so we're going to have to do that. So if I take it and move that 2 over by subtracting, to add and subtract fractions, we have to have a common denominator. Common denominator would be the x plus 3. So that 2 is understood to have a denominator of a 1. We want it to be x plus 3, so however we change the denominator, we got to change the numerator the exact same way. So multiplying, we would have x minus 1 minus 2x minus 6 over that common denominator. And when you combine like terms, we would get negative x minus 7 over x plus 3. Now if you'll look, we did a problem very similar to this 2 problems ago. It was the exact same fraction, except instead it was less than or equal to 0. So from there you should remember our critical values were negative 7 and negative 3. When you plugged in values, and you can go back and check it, it's 2 problems ago. When you plugged in values, notice you got a negative, positive, negative. All of that's going to be the same. The only thing that's going to change is your answer, because this time they're wanting to know where it's greater than 0. Greater than 0 is positive. So same number line, same results. This time though we want to know where it's positive. It is positive in between negative 7 and negative 3.